Okay, we ever take another interesting integral from the MIT Integration Bee 2010, problem number 10. We've got the integral from 0 to pi over 4 square root tan x dx. Okay, this was a really good one. I actually know two different ways to do this. So I'm going to do two videos, two different methods. I don't really know which one I like better. One's got more of a trick and one's more straightforward. We're going to do, today for this one, I'm going to do the more straightforward method. I'm just going to do a u-substitution. I'm going to do the u-substitution for the whole thing here. So we'll call u equal to the square root of tan of x. And then what I want to do from here is go ahead and try to solve for x. So we can square both sides and we'll have u squared equal to tan x. Then just taking the inverse, we have x equal to arctan of u squared. I'll go ahead and take the derivative to get a dx value. So what's going to happen, we have dx equal to 1 over this thing squared. So we're going to have u to the fourth plus 1, but then I need the chain rule. Derivative of this is going to give me a 2u. So now we'll go ahead with this substitution over here. First, evaluating pi over 4. Tan of pi over 4 is just 1. So square root of 1, 1 for the upper bound. Plug in 0. Tan of 0 is just 0. Then again, this whole thing is going to be u. Our dx is all this. So we're going to have times 2u over u to the fourth plus 1 du. But now from here with u to the fourth in the denominator, this is a little tricky. So I want to clean this up. I'm going to multiply numerator and denominator by 1 over u squared. What's going to happen with this now is then we're just going to have 2 in the numerator. We'll have 2 du. This is going to become u squared plus 1 over u squared. But now here, for this thing right here, I can actually factor this two different ways. I can factor this as, we can do it as u plus 1 over u squared. When we do that, we get an extra 2, so we just subtract that off. And then the other way I can do this is I can do u minus 1 over u, and then you get a minus 2, so we can add a 2 to make it work. So with this, what I'll do is I'll break this up into two integrals. One's going to have this thing in the denominator, the other one's going to have this in the denominator. So let's see how this works. We're still going from 0 to 1. So we'll have the first one's going to be u plus 1 over u minus 2. And then for this second one, we'll have this one. So this is going to become u minus 1 over u plus 2. And what I'm trying to do here is set up a substitution. Each of these, we're going to want a substitution here for this thing and a substitution here for this thing. So we'll use different variable names. I'll call this one t, I'll call this one w. And now I'll just take a derivative on both these. So first we're going to get a dt value over here. Derivative of u is 1. Derivative of this is going to be minus 1 over u squared du. Then over here, same kind of thing. For dw, we get 1, and this is going to become a plus over here, 1 over u squared du. But now what I want to do is force each of these to become the numerator in each of these integrals. So we'll have this one, we're going to force this one here, 1 minus 1 over u squared. We have our du, of course. And then over here, we'll make this one 1 plus 1 over u squared. But now at this point, the concern is, do we change the whole thing? Do we break this? Well, keep in mind, these denominators are both the same thing. We just manipulate it. So we have common denominator, you add them back together. You can add this and this. When you do that, the 1 over u squareds are going to cancel. 1 plus 1 gives this 2 here. So we didn't change it at all. Now keep in mind, it won't always work out this nicely. Sometimes you have to multiply by a constant in front. But in this case, it works fine, and we just get back to our 2. But now I'll just go ahead and make the substitution, and then we can integrate and finish it off. First, let's update our bound. So taking 1, if you plug 1 in here, you're going to get a 2 for this upper bound. And then plugging in 0, you'll have a 0 here, and then 1 over 0, so we'll write this as just infinity. Then making the substitution here, we're going to end up with dt over t squared minus 2. And then for this other one, really similar, updating the bounds, plug 1 in here, we end up with 1 minus 1, or 0. Plug 0 in, this is actually going to become minus infinity. Then transforming this whole thing in the numerator is going to be just dw. And then here we're going to end up with w squared plus 2. For this plus 2, I'll rewrite this. What we can do here is write this as square root of 2 all squared. And then over here I can do the exact same thing. We can write this 2 as square root of 2 all squared. But what I actually want to do here, I'm going to reverse the sign on this by multiplying by a minus 1. And then pulling a minus out, I can use to swap our bounds just so we get the larger value at the top. But now from here, for this integral, I just want to use the formula we have over here to the right in order to simplify this, where our a value is going to be this square root of 2 right here. So doing this, we're going to have 1 over 2 square root of 2. Natural log, again, using our a value, we're going to have square root of 2 plus t, where we have x there. And this is going to be square root of 2 minus t. And this is just going to be evaluated from 2 to infinity. And then for this second one, this is just going to be our arctan formula. So this formula is going to work pretty similar. We're going to have 1 over square root of 2. That's going to be arctan, this w over square root of 2. And we just need to evaluate this from minus infinity to 0. Now going ahead with this, first evaluating at infinity, what's going to happen in here, this is going to be a limit, and it's going to be going to minus 1. With the absolute value, it becomes ln of 1, so this first term is just going to be 0. And then for the second part, we need to plug in a 2. So we're going to end up with this 1 over 2 square root of 2. Then we'll have absolute value square root of 2 plus 2 over square root of 2 minus 2. We'll clean that up later. Then next for the second part, evaluating arctan at 0, that's just going to be 0. Then we'll bring across this 1 over square root of 2. When we plug minus infinity in here, arctan at minus infinity, that's going to give me minus pi over 2. Minus times minus is plus. So at this point we could almost leave it, but let's actually try to get a little simplification. On this, what I'm going to do, I want to rationalize the denominator on this thing. So doing that, I can multiply numerator and denominator by square root of 2 plus 2, like this. When I do this, I can leave the numerator as square root of 2 plus 2, all squared. Doing this in the denominator, we get 2 minus 4, or minus 2. But we're going to be inside the absolute value here, so I'm just going to change this to a plus. Then coming back to our natural log here, I'm going to split this up. I'm going to write this minus 1 over square root of 2. I'm going to take a 1/2 and put it in the exponent. And now that this is positive, I'll drop the absolute value. So we'll have this square root of 2 plus 2 over 2. And then this is squared, and we're going to have this 1/2 in the exponent. Well, then with this, what I can do, we'll bring this back. We'll have minus 1 over square root of 2. Now that we have the half exponent, I can distribute this in. And so then now, because this is squared, we can write this as square root of 2 plus 2 over square root of 2. Then I can divide the square root of 2 in. We'll have minus 1 over square root of 2, natural log. Here, this is going to become 1 plus 2 over square root of 2. I can write that as just square root of 2. So now we can just take this and put it back in here and finish it off. But now at this point, I can just reorder it and put it all together. So for my final solution, we're just going to have pi over 2 square root of 2 minus natural log 1 plus square root of 2 over square root of 2, and that's it. Okay, there you have it. Tricky problem from MIT 2010. Thanks everyone for watching. Have a good day.